Thank you very much. So in thinking about how to most usefully give you a feel for my research, I decided that rather than trying to be comprehensive, which would anyway require covering about a project per minute, it's more fun to focus on a specific theme weaving through much of my work, and so try to give you a sense of my perspective. So I'll tell you about my favorite objects in physics, which, as you can guess from the title, are black holes. I have explored various aspects of black holes in astrophysical, relativistic, string theoretical settings, but the predominant context has been within holography. So I'll also tell you a little bit about holography and further focus on a subject I have been fascinated by lately in this context, namely entanglement. Now that might seem like quite a disparate set of topics, so let me first orient you to the structure of my talk. Well, most of us have probably heard about black holes long before becoming physicists or mathematicians, but the variety of ways in which black holes appear in popular culture or science fiction is nothing compared to how amazing and multifaceted they actually are in real life. So to give you a sense of this, I'll first review various guises of black holes. Now the study of black holes has underpinned the developments leading to the renowned ADS-CFT correspondence, which I'm sure most of you have heard about. This has spurred a vast research program over the last 17 years, so I'll only highlight some of the key aspects of the correspondence and quickly indicate my own contributions to the field. I'll then focus on a specific aspect of ADS-CFT concerning a central notion of quantum mechanics, which is entanglement. And, well, this is not a random choice. I have always been deeply fascinated by quantum effects. And, in fact, the underlying motivation for all of my work has been to elucidate quantum gravity. So if I still have time at the end, I'll try to briefly tell you about some of the exciting things that have been coming out in recent years, where there's hints of some deep connection between entanglement and space-time geometry. Okay, so let's start with black holes. So, as you know, 100 years ago, Albert Einstein formulated his beautiful theory of gravity, general relativity, which says that gravity is simply a manifestation of space-time curvature, and matter in turn curves space-time, so that black holes are a robust prediction of the theory, formed whenever sufficient amount of mass gets compressed into a small enough region. Now in nature this actually happens all the time, typically when a massive star reaches the end point of its thermonuclear burning phase and collapses. Now once the black hole is formed, nothing can classically escape from it, as indicated by these light cones. Here I'm drawing time going up and suppressing one spatial dimension. So in Newtonian language, you would have to exceed the speed of light, or in GR parlance, space-time becomes warped enough to disallow causal communication with the exterior. Now this might seem rather strange, this causal structure, and indeed, though Carl Schwarzschild wrote down the first black hole solution only months after Einstein's paper, the physics of it wasn't understood until much later. And in fact, John Wheeler coined the term black hole only in the 60s. Now, more severely still, inside the black hole, curvatures can become arbitrarily large, signaling a breakdown of the classical GR description at the so-called curvature singularity. So this fact has actually made black holes seem unphysical and largely ignored for about half a century, until astrophysical observations caught up and propelled the field into what some call the golden era of black hole research in the 70s. So I can't help thinking that actually we're entering another golden era right now. Okay, so by now, most astrophysicists would agree that black holes are real objects out there, even responsible for some of the most energetic processes in our universe. And in fact, the modern day telescopes might be actually able to resolve the actual black hole horizon. The surface of the black hole is called the event horizon. It's the defining feature. So, well, the attributes, nevertheless, are pretty extreme. So just to give you a sense of scales, the densest known regular astronomical object is a neutron star, whose density is such that, well, some 2 tablespoons of it would weigh as much as a kilometer cube slab of lead. Black holes are, of the same mass, would be about 4 times smaller. So a solar mass black hole would have horizon radius of only about 3 kilometers. And if the entire Earth collapsed to a black hole, it would be only about this big. Nevertheless...
And that's assuming the density of a neutron star.
Okay, average density.
Is it?
Average.
That's what you're assuming, though.
No, now I'm talking about black holes. So this is independent of neutron stars. The neutron star was brought in by comparison.
Yeah.
So black hole would be much denser.
Black hole.
But then the density is not a good language to use at that stage. But if you average naively, how much mass fits into one volume. Okay, but it's remarkable that despite the physical presence in nature and the rather unusual attributes, black holes are actually described mathematically very simply. In fact, Chandrasekhar called them the most perfect macroscopic objects there are in the universe, because the only ingredients in their constructions are concepts of space and time. Now, this mathematical elegance rendered them to be very useful theoretical laboratories, and over the years our explorations have been richly rewarded. So black holes turn out to lie at the heart of many profound dualities, such as the ADS-CFT correspondence, which I'll come to shortly. More remarkably still, and in a rather subtle way, black holes actually turn out to be related to ordinary systems, such as fluids. So that means that they're not only relevant for astrophysics and cosmology, but black holes now permeate more, wide-ranging subjects such as fluid dynamics, condensed matter physics, nuclear physics, and even more surprisingly and subtly, information theory. So I'll come back to all that. But, well, that might seem like an amazing list already, but that's not the end. I think, in fact, we have barely seen the tip of the iceberg. Some of us believe that black holes, they actually hold a key to quantum gravity. So, as you know, the 2 pillars of 20th century physics, quantum mechanics and general relativity, while individually well tested and understood, are mutually incompatible. So that manifests itself most strongly inside black holes or for the universe as a whole, but it means that we still are missing the most basic, sort of an essential aspect of our understanding our universe. So the quest for quantum gravity then means to develop a complete and consistent framework which would enable us to answer questions pertaining to origin and fate of our universe, the fundamental nature of space-time, and so forth. Now, black holes have this privileged status for many reasons, apart from the fact that their full description obviously does require quantum gravity. So, to give you a better feel for that, let me tell you a bit more about black holes. All right, so I said that black holes are described mathematically very simply. That's actually a severe understatement. It turns out that a stationary black hole can be completely characterized by just 3 parameters, corresponding to their mass, angular momentum, and charge. And but this is obviously very different for ordinary objects, which would need much more defined specification. So these three parameters characterize the full space-time, including the location and properties of the event horizon. So the most important of those are the horizon area, surface area of the black hole, and something called surface gravity, which you can think of as a force exerted at infinity to hold a unit mass object suspended just above the horizon. Now it turns out that these characteristics, these features behave very much like according to ordinary laws of thermodynamics. So if you, the surface gravity is constant over the entire horizon of a stationary black hole. If you throw something into a black hole, the mass of the black hole grows in proportion to the horizon area, plus other work terms. And the area can never decrease, nor can you achieve zero surface gravity in any physical process. And so you can see that here the surface gravity plays the same role as the temperature in the ordinary laws of thermodynamics. And similarly, the area plays the same role as entropy. So since energy and mass are already identified, it's natural to identify the surface gravity with the temperature and the horizon area with entropy. Now that might seem very odd because I said nothing can escape from a black hole, so how can it possibly have any temperature? How could it radiate? And moreover, if black holes are described that simply, how could they possibly have any entropy? Well, the answer is applied by quantum mechanics. So the fact that entropy, area of a black hole can have something to do with entropy was motivated by Bekenstein, by Granitin experiments that involved lowering things into black hole. But the main substantiation came with Hawking's semi-classical calculation, which showed that black holes indeed do radiate with a black body spectrum at a specific temperature, and that allowed us to fix the constants of proportionality here and show that indeed temperature is related to the surface gravity, which then means that entropy is related to the area. So I have reinstated the usually ignored fundamental constants of nature here, just to emphasize that these relations are fundamentally rooted in thermodynamics, in special relativity, in gravitation, and in quantum mechanics. Now, from statistical mechanics, we're used to thinking about entropy as counting the number of microstates. So the main question here is, what are the microstates of the black hole? Now, how many do you need? Well, the reason that this wasn't actually observed before is that for, say, solar mass black hole, the temperature would be tiny, something like 10 to the minus 7 Kelvin, but the entropy is enormous. The entropy would be something like 10 to the 77. So that's some staggering, 40 orders of magnitude more than a neutron star. So where are all these microstates? It's a humongous number of microstates. And, well, we don't have the answer yet, but it has been a very fruitful research program over the years. And in fact, Steve here is one of the experts. But let me not, detour into that too much, but instead discuss the implications of this. Okay, so, of course, if black holes radiate, the black hole area shrinks, and you might say, well, that violates the second law. But the semi-classical, of course, the theorem is fine. It's just that the semi-classical effects don't satisfy the energy conditions that the theorem assumes. But instead, there's a generalized second law that the combined matter plus black hole entropy has to increase. And that has interesting implications. One of them is the so-called Bekenstein bound, that the entropy of a matter fitted in some region of characteristic size R with some energy E, when it's weakly gravitating, has to be bounded by this product. More interestingly, for for spherical systems, which can be strongly gravitating but should be slowly evolving, there's the spherical entropy bound, which says that the matter entropy packed in a spherical region with some volume and some surface area A is actually bounded by the area, quarter of the area, rather than the volume. Which follows from the fact that, well, if all of that matter collapsed into a black hole, it could not have any more entropy than that. So in fact, black holes are the most entropic objects in the universe. Now this might seem very odd, because we're used from local field theory and thermodynamics to think of entropy as an extensive quantity. You know, you think if you have a certain volume, you can pack in some information. If you have twice the volume, well, you can pack in twice the information. Now, what that intuition misses is the effects of gravity. After a point, if you try to pack in any more information, the whole thing collapses to a black hole. So, now, you might object that, of course, both of these actually have limited regimes of validity, which is true, and you can find counterexamples outside of these regimes, that was remedied by Busso by covariantizing this entropy bound. So there's a covariant entropy bound, which is valid robustly, and rather intriguingly uses the full space-time, the full Lorentzian space-time structure, of rather than considering volumes at a given time, uses something that Busso called light sheet, which is just a null surface that's generated by perpendicular light rays emanating from some given surface, such that those light rays have to keep converging. And then the entropy bound says that the entropy crossing such a light sheet cannot exceed the area of the surface. Now typically, if you have a co-dimension 2 surface, there's always 4 null directions, and it's typically the ones that are ingoing that are shrinking, that would be light sheet. But if you have a strong gravitational field, like inside the black holes, even these outgoing ones would actually be bent in and shrink. So this concept has a close connection to sort of how strong gravity is. Now, this got elevated to the holographic principle that any theory of gravity should respect this entropy bound. And, well, this doesn't specify how the degrees of freedom are represented, but it puts a very sharp bound on how many there can be, and implies a physical equivalence between two theories that live in different number of dimensions. And that sounds very weird, but we do, of course, have a concrete realization, which is the well-known ADS-CFT correspondence. So this beautiful correspondence was formulated by Juan Maldacena in 1997, and based on, using the framework of string theory, where he considered two different descriptions of certain fundamental objects called D-branes, which in some regime behave like a higher dimensional black hole. And the upshot of this is that a string theory, which is among others a theory of gravity, is physically equivalent to a certain gauge theory, which is a conformal field theory, describes the same physics in very different language. Now, the two theories live in different dimensions. The string theory lives in the bulk of anti-de Sitter space, which is a negatively curved maximally symmetric space-time, while the gauge theory lives on the boundary of this ADS. So in the early days, people like to think of this in analogy with a soup can. String theory is the soup inside, and the field theory is the label. But unlike ordinary soup can, where the label just gives you a rough idea of what's inside, here the label actually is everything. So the key aspects of this are that...
If you eat that soup, you might starve.
Oh, there's a lot contained in that. Very nutritious. So the key aspects are that a theory of gravity, quantum theory of gravity, is not a non-gravitational one, which provides an excellent sort of framework to ask all the long-standing quantum gravitational questions by recasting them in a non-gravitational language. A related aspect is that the theory is holographic in that it respects the holographic principle. H theory lives on the boundary in 4 dimensions. Not that it has anything to do with real holograms. In fact, I think a better analogy would be a stereogram, like this 2D image, which if you look at in a certain way, you see a 3-dimensional picture coming out of this. Now, in this case, it arises due to correlations between pairs of these blotches that your eyes interpret as parallax. In the real ADS CFT, it's of course infinitely more complicated, with correlations between all points, and instead of having these blotches, you have a very sensible CFT picture, quite different from the higher dimensional emergent gravitational image. Alright, so apart from mapping a gravitational theory into a non-gravitational one and respecting the holographic principle, the ADS CFT is also a strong weak coupling duality, which means that we typically don't have good computational control over both sides simultaneously. It also means that, that's partly why, preposterous as the correspondence may sound at first sight, it's not obviously wrong, because our intuition built on perturbative field theory doesn't apply in this case. So it has been an enormously useful tool over the years. So because it's a strong weak coupling duality, when the string theory is under control, the field theory is strongly coupled. And so we can use calculations in gravity to learn about strongly coupled field theory, as has been utilized and very successfully implemented in these ADS quantum thermodynamics and ADS condensed matter theory programs. And in fact, that's where most of the success and applications have been coming from. But one can also go the other way. One can use the gauge theory to define and study quantum gravity in ADS, which is tremendously, it's fair to say that progress in that direction has been less spectacular than in the other direction, but I think we're on the brink of really starting to find that very, very, very much. But of course, the prerequisite for all that is to have a good understanding of the mapping between the two sides, the dictionary, if you will. All right, so let me tell you some key aspects of that dictionary. Well, the first thing that you might ask, most naturally, when you encounter a holographic duality, is what feature in the lower dimensional theory mocks up the extra dimension. Right? In ADS CFT, a partial answer comes from the scale radius duality, also called UV-IR duality. The small scales, UV in the field theory, is captured by large radius, or in that sense IR, in the ADS. So Susskind and Witten formulated this in terms of sort of regulating, and also identified that if you have, so this would be a boundary where the field theory lives, if you have some excitation, some physical distance z from the boundary, the description of that excitation has roughly a scale size that's proportional to z. This actually comes up, rather naturally from the geometrical structure of ADS, which is very conveniently visualized in terms of these Escher goings. So here, this is like looking at my soup can from top, like looking at the lid, taking constant time slice, and the previous picture is just zooming into the asymptotic region. And each of these fish, so this is the boundary, and each of these fish is actually same proper distance. So if you have one of these points in the bulk, say this one, then the characteristic size of the excitation in the field theory that's supposed to be dual would be one that's spanned by this tangent arc. Now this one thing I really like about this particular issue drawing is that it illustrates another important fact, that this arc is, of course, not unique in this global ADS picture. So you can take, for example, this arc, or this one, or any of the other ones. So this has been actually recently used to sort of put forth a conjecture that the mapping, the local bulk mapping in the field theory is like an error correction. There isn't a unique place where you could say this bulk point gets mapped into a precise region. Okay, now this UVIR, or scale radius duality, has some, has some very interesting subtleties, which I won't have time to tell you about right now, but it does bring a lot of intuition. So if you think of, let's not take just the boring ADS, but let's take a black hole, and that would deform the picture right here, and ask how would some particle that falls in the bulk from the boundary into a black hole, how would that look in the field theory? Well, what we would guess from this is that you start with a localized excitation that spreads and thermalizes, which is exactly what happens. It gives a very nice picture. A related entry in the ADS CFT dictionary is that asymptotic fall-off of bulk fields can be characterized in terms of expectation values of local operators in the field theory. All right. Another useful ingredient in the dictionary is the relation between bulk geometries and CFT states. So the geometry in the bulk just has to be asymptotically anti-de Sitter, but otherwise it can be anything that satisfies the field equations. And similarly in the field theory, we can consider any excited states. So if you consider the vacuum, the ground state of the field theory, that corresponds to pure ADS, nothing in it, the maximally symmetric space-time. But if you have some finite mass deformations inside, that would result in some non-zero stress energy momentum tensor in the field theory, characterizing some excited state. So the further the deformation from ADS, the more excited the state is. And most sort of deformed case, highest excitation, is when you collapse a black hole. So a black hole in the bulk corresponds to a thermal state in the field theory. So this can be actually understood at a rough level as just an endpoint of a typical evolution. So you put in some high excitation in the bulk, and it collapses into the black hole because of, combined effects of gravity and this negative cosmological constant. Whereas in the field theory, you don't have gravity, but things tend to thermalize. And they thermalize to the same temperature as the Hawking temperature of the black hole. But of course, that's too coarse-grained for what we really want to know about black holes. They have all these cool properties, so how do we see them in the field theory? We want to ask, how does the field theory describe physics behind the horizon, if it does? And what is in particular, how does it describe the black hole singularity, where classical gravity breaks down? So the CFT should provide answer for what happens. What is the description of the causal structure, and so forth. So as a starting point, one wants to at least understand what about time-evolving geometries? How is the time evolution captured on the field theory side? So for small deviations from equilibrium, this was actually well understood from the early days of ADS-CFT. If you kick the black hole a little bit, it will ring and settle back down to its equilibrium by these so-called quasi-normal modes, which are characteristic time scales and frequencies independent of what was the initial perturbation. And so we calculated these quasi-normal modes and predicted the timescale for the approach to thermal equilibrium. Now, this was subsequently generalized to calculate the full set of response properties of the horizon from a linearized calculation, which then tells us the various transport coefficients in the fields here. And this is all at the linear level, but you can do better. So for those of you who are a bit familiar with the notation, let me just quickly mention the mathematical description of all this. So the bulk geometry is specified by a bulk metric, G, and the boundary state is characterized by the stress energy momentum tensor, T, which can be read off from the asymptotic falloff of this metric. And now if you have a state where the variations in the spatial and temporal directions are sufficiently slow, such a state describes a fluid. All right, so this will be some fluid stress tensor. Now, the dynamics of this, well, in the bulk, the dynamics of the bulk geometry are specified by Einstein's equations with negative cosmological constant. And here I'm putting no bulk metric. Okay, so this characterizes the curvature of the geometry. The boundary dynamics is specified by stress tensor conservation, supplemented by constitutive relations, which specify the stress tensor in terms of the fluid variables like temperature and velocity and so forth. Okay, so because the two sides are dual to each other, you might think, well, maybe there is some relation between these two sets of equations. So this, by the way, I should say, if you have a non-relativistic dissipative fluid, this would be the standard Navier-Stokes equations. Or Einstein's equations, you have Navier-Stokes equations, are they related to each other? Well, it's not a trivial consequence of ADS-CFT because the regimes of validity of these are slightly different. Moreover, the mapping between the boundary and the bulk is highly complicated, as we have seen on the scale radius duality. And besides, this is a highly, it's a second order coupled, highly nonlinear set of PDEs. So it's not clear that there would be a relation, but we have seen that there is one at the linearized level. And in fact, the beautiful thing is that there is indeed a direct relation at the nonlinear level as well. So this goes under the name fluid gravity correspondence, which we've developed, I guess, almost 7 years ago. And so let's consider, this applies to configurations which are in local equilibrium, meaning the variations in the boundary directions are slow, but they can have arbitrary amplitude. So the boundary is described by some fluid, with the fluid temperature and velocity being functions of the position and time. So because we have some temperature, that means in the bulk we're dealing with some black hole, but now with a horizon non-uniform, with no symmetries, evolving, the horizon is sloshing around in some way until it eventually settles down to the global equilibrium through dissipation. So we have constructed, for any fluid flow, we can construct a solution of this dynamical black hole whose horizon then precisely mimics what the fluid is doing. Now this is, of course, easily said than done because, as I said, the equations that the bulk obeys are highly nonlinear PDEs, and in fact, solving Einstein's equations exactly, one can do only for, if you have sufficient amount of symmetries. Otherwise, one could try to linearize Einstein's equations and solve perturbatively near a known solution, but that's not quite what we want to do. Or resort to numerics, which actually numerical GR has undergone quite a revolution recently and can do lots of impressive stuff, but solving for a generic, perturbation of a black hole far from equilibrium would still take months on a dedicated supercomputer cluster. So what's amazing is that we can actually get an approximate solution to arbitrary accuracy by the following trick. We use the fact that we have slow variation in the boundary directions, and we can expand Einstein's equations in boundary derivatives. So conceptually, this is a cartoon of what we want to do. We have so suppose this is the bulk radial direction. Boundary would be somewhere here. This would be one of the boundary directions. This function would be the horizon position, which is also directly related to the temperature of the black hole. And the color coding could be, say, one component of the velocity. So we want to think of this varying black hole as piecewise or tube-wise uniform black hole, and patch these tubes of different size, different velocity, different temperature black holes together consistently. And it turns out that you can do this order by order in this boundary derivative expansion. So we did this to second order, and that allowed us to obtain the second order transport coefficients for this conformal fluid that the black hole describes. And so that you can now go and compare with real life fluids. And moreover, you can, once you have the solution, you can study its properties. So you can study where the event horizon is, and you can solve for the location of the horizon, again, order by order, and the area form on the horizon back to the boundary gets a natural entropy current for the field theory, which automatically has no negative divergence. So satisfies the second law due to the area theorem for the black hole. All right, so since then, there have been many, many generalizations and many applications. You can do this not just for the relativistic conformal fluid, but you can have charges, you can have superfluids, non-conformal fluids, non-relativistic fluids. You can add boundaries, you can force the fluids, you can do it in other dimensions, and so forth. But unfortunately, you can't still do it for the things we're familiar with from really everyday life, especially non-Newtonian fluids. But it will be interesting to see how far one can actually push this. And so that has already many applications, obviously to black hole physics, because now we have, instead of a few parameter solution, we have an infinite class of non-uniform evolving solutions, approximately. Applications to fluid dynamics, because we can geometrize the fluids. So we can study, for example, long-standing questions like turbulence by looking at the gravitational system. We can look at the transport properties of the fluid, and so forth. All right, so I was going to talk about one application, but I'm going to run out of time. So let me skip over this and continue to my last part of the talk, which is what have people done with ADS-CFT. And broadly speaking, there have been two sort of main directions. One is what I would characterize it as applied ADS-CFT. You take some specific system you're interested in, and you describe it in its dual language, all right, and study its properties where it's more convenient, where you do calculations that you couldn't have done directly otherwise. And you can study what I would call as sort of fundamentals of ADS-CFT. How does the duality work? What is the mapping between the two sides? This entanglement, holographic entanglement entropy is the quantity I'll focus on, actually very naturally fits into both of these categories. And the particularly interesting aspect of it is the relations to quantum gravity. So, just to tell you a bit about entanglement is, of course, not only a crucial feature of any quantum system, but it's perhaps the most non-classical manifestation of quantum mechanics. So, mathematically, entanglement is present when the composite state of a quantum system cannot be described as a product of the states of the individual subsystems, which has been quite a, well, conceptually quite a confusing thing for people. So Schrödinger characterized it as the best possible knowledge of a whole does not include the best possible knowledge of its parts. And indeed, that aspect is still behind the most pressing paradoxes in this area even today. But people have come to realize that, well, it's not just some very crazy quantity, it's actually a new quantum resource for tasks that can't be performed by just using classical resources. So this has propelled entanglement into a forefront of course, quantum information and quantum computing, but even quantum body systems and quantum field theory and so forth. And the thing that I find the most fascinating is these connections to geometry. So just to give you a feel, very briefly, for a very baby problem, the simplest thing you might have, just a 2-qubit system, say 2 electrons, A and B, which can each be in some superposition of spin up and spin down. So a simple product state where A is up and B is down can be written like this. A more complicated product state where each of them is in some superposition is written in some way like this. But a general state with arbitrary coefficients here, just subject to the normalization, it need not be writable as a product state. And when that is the case, that state is entangled. So the maximally entangled state is an EPR pair, or Bell pair, which is written like this. So to characterize entanglement, a very useful quantity is the entanglement entropy, which characterizes, if you just have access to, you separate your system into 2 subsystems, if you just have access to one of them, you can formulate the so-called reduced density matrix, which is obtained by tracing out the stuff you don't know about, the complement of the region. And you define the entanglement entropy as the von Neumann entropy for this reduced density matrix. Okay, so this is like a quantum analog of the Shannon entropy. So for the 2-qubit system, if you have the Bell pair that has a maximal amount of entanglement, in this case just log 2, whereas if you have the pure state, the non-entangled one, the entanglement entropy would be 0. And for generic states, it's something between 0 and its maximal value. Now, here it's very easy to calculate because you just, you just add the eigenvalues of the reduced density matrix. Of course, for more interesting systems, it's far, far harder. But you can define entanglement entropy much more generally. All you need is to be able to divide your total system into 2 subsystems such that the Hilbert space can be written as a product. So for example, if you take a spin chain, you can consider some set of the spins, define them as your region, and the rest as the other one, and then you have this, you can define the entanglement entropy this way. So here, there is no physical partition. It's just our choice of which region to focus on. You can do it for some quantum many-body systems, where, say, you consider all the spins within some region. And more interestingly, you can, if you take the continuum limit, you take a quantum field theory, a local quantum field theory, it's very natural to specify a certain spatial region, and you can then define entanglement entropy for that spatial region. So you choose some region bounded by what I'll call the entangling surface, and for all of these systems, then the entanglement entropy is this von Neumann entropy of the reduced density matrix. Now, this has lots of applications. Again, let me just, in the interest of time, let me just keep going, speed up a bit. But it's a really useful quantity. That's great. But the bad news is that it's very tricky to deal with, as you might guess from its intricate quantum origin. So it's very non-local quantity. It's very sensitive to the environment, so it's very intricate. It's difficult, if possible, to measure because it's non-local, and it's very difficult to actually calculate, especially when you're trying to do it in a strongly coupled system. But we have been trained by ADS-CFT to ask, whenever encountering some problem in strongly coupled field theory, whether ADS-CFT can come to the rescue, and in fact even expect the answer to be yes. So in this case, if we had a strongly coupled field theory with some region on that we want to calculate entanglement entropy for, we could put the system on a boundary of bulk and ask, is there a bulk quantity that gives you the entanglement entropy of this region, which would then be called the holographic entanglement entropy. Now, a priori, this might seem like quite a daunting task because you're asking for some very complicated quantity and parsing it through this highly intricate and non-local mapping. So a priori that seems completely hopeless, but the miracle is that the answer is yes. It actually is described, not only is it described in the bulk geometrically, but in a very simple way. So in 2006, Ryu and Takenagi proposed this for static configuration. They proposed that the entanglement entropy of this region is captured by the proper area of a certain dimension 2 bulk surface, which is anchored on this entangling surface. That certain surface is a minimal one, meaning to minimize its area at the constant time slice. And the entanglement entropy is given by quarter of this area in Planck units. All right, so this we have seen this type of formula before. This is very analogous to the black hole entropy area relation, except that here we're talking about entanglement entropy on the boundary, and we're talking about a surface that ends on the boundary rather than a black hole horizon, although in both cases it's the horizon at a certain time is also a minimal surface. Now, in all the pictures I have been showing so far, I have been drawing the boundaries at some finite distance, just to fit it into the picture. But of course, in reality, it's infinitely far away. And so the surface wants to hang into the bulk like this and reach the boundary perpendicularly just to minimize its amount of time it's in this infinite region. And that also means that its area is infinite. Now that's a feature rather than a bug, because even in the field theory, the entanglement entropy is infinite. Coming from the UV divergence is the entanglement just across the entangling surface. And in fact, there's a lot of physics in these infinities. You can systematically expand out the infinities, and the leading infinities in this case is the area of this entangling surface. Subleading ones give you sort of the geometrical features of this and so forth. Now there's a large body of evidence for this Ryu Takenagi proposal. Again, in the interest of time, I'm going to skip it, but I'll just want to tell you that it has already geometrized the notion of entanglement very usefully, in the sense that there are many important theorems that were quite hard to prove directly on the field theory side, and were just beautifully simple on the gravity side. So this geometrization really works very well. And, this set of arguments for it culminated in arguments by Lefkowitz and Baldacino, which used Euclidean path integrals to essentially prove this. But we have to, of course, face up ultimately to the fact that we live in a Lorentzian space-time with time. And entanglement entropy is well defined for time-evolving situations, but the prescription given by Ryu and Takenagi does not apply for time-evolving configuration states. So in Lorentzian geometry, one trouble is that you can, of course, decrease the area arbitrarily by rippling it in the time direction. And moreover, in the time-dependent context, there is no natural constant time slice. That's just some coordinate artifact. All right, so for more general geometries that depend on time, we have to covariantize, we have to generalize the prescription in a well-defined, geometrically well-defined way, so that it's applicable in general. Now, we have, so very soon after the proposal, we have tackled this problem, and we initially thought of various possible natural generalizations. The most obvious one would be to promote a minimal surface to an extremal surface, one where you're extremizing the area rather than minimizing it, which is a natural, you can think of it as a higher dimensional version of a geodesic. Now, many things in the Ryo-Takanagi proposal were very easy to prove due to this minimization. So if you're sort of wedded to the trying to keep a minimization character of it, you could do something like take a special geometrically preferred space-like slice of the bulk, say one that maximizes the proper volume, and on that take a minimal surface. That's possible. That's fully covariant. You could think that, well, we have seen that null rays are somehow special and very telling, so maybe we could take a surface which has zero null expansions, which is sort of the furthest light sheet you could have that reaches the surface from which the light sheet reaches the boundary, so the furthest one. Or you could have some even more, a construct that's very deeply rooted in causal structure, called a causal wedge, and take its rim. I'll talk about that a little bit later. So here are, in pure radius, of course, all of these coincide, but in general spacetimes, like this one where you collapse a shell, collapses into a black hole, I have sketched two of these, the extremal surface and this causal wedge rim. They certainly differ. So studying which of these prescriptions fit with all that we know, we realized that, well, first of all, so our proposal is the extremal surface, which happens to be the same coincident surface with the one with the zero null expansions. So this proposal now became known as the HRT prescription and is the one that people use to study entanglement entropy. And curiously enough, this causal wedge rim lay dormant for about 5 years until we took it up again, and we formulated a quantity which we call the causal holographic information as its area, which actually has, well, it's a very nice natural construct in the bulk. We don't know how to construct it from first principle, or what it is from first principles in the field theory, but it's something that's probably quite important in the field theory as well, so it's an interesting direction to understand what it is. All right, so the prescription then for the entanglement entropy is that you take an extremal surface in the bulk that's anchored on this entangling surface. And there are a couple of other more technical provisos that I'm not going to go into. Now this is well-defined, very robustly well-defined for arbitrary geometry, okay, with arbitrary time dependence. So it's as equally robust as in the field theory. But now it's harder to prove because we don't have the nice Euclidean techniques that we could have used for the Ryo-Takanagi. So one can ask, so far in absence of proof, is it consistent with all the main principles that it should be consistent with? So one natural question, since we have introduced time dependence, we should ask, is this prescription still consistent with the field theory causality? And the answer is yes, but so what do you expect from CFT causality? Well, if you have, so this is just a boundary space-time, you single out some region, and you can ask, what does the entanglement entropy of that region depend on? The answer is, it depends on the full domain of dependence of this region, but if you make some, suppose you change the state within this, let me just put the option, within this region, that cannot change the entanglement entropy, because you could imagine that this slice was already sort of before that change. Similarly, if you do any deformation of the state in this region, or in the future, you cannot change the entanglement entropy. So the entanglement entropy for this region can only be deformed by something that happens to the past of the entangling surface. So this naturally decomposes the space-time into 4 regions, the future and past of this entangling surface, which is in this case just these 2 points, the domain of dependence of the region of interest, and the domain of dependence of its complement. Now in the bulk, you might want to ask, well, is the extremal surface actually consistent with that? Right, so first of all, well, we have shown that it has to be outside of this causal wedge. So the causal wedge is the set of points which are causally connected both through past and future to the domain of dependence of this region. But it has to do more than that. It has to lie in what we call the causal shadow of the entangling surface. So the causal shadow is a region which is causally disconnected both from the domain of dependence of the region and its complement. Okay, so this is a requirement on the extremal surface in any geometry, so any state in the field theory, that surface has to satisfy in order to capture entanglement entropy. And we have shown that this is indeed the case mathematically by using simple properties of the null geodesics in the bulk. But it's quite a non-trivial condition for this holographic prescription, and it's not something that was guaranteed. So already the static case for which Ryu and Takayanagi's prescription was applicable satisfies this condition marginally. Meaning, so here is a null plane in pure ADS, and if you take say one of these extremal surfaces, these are space-like geodesics across, you can send a signal to deform that surface only in such a way that that signal would also deform the entangling surface. So if you deform this in the bulk a little bit, you're in danger of violating this. But nevertheless, it is satisfied. And there is a natural decomposition of the bulk that you can make that mimics very much the boundary decomposition. And this allowed us to define a quantity that's very naturally associated with this region called the entanglement wedge. So we propose that this entanglement wedge is the natural dual of the reduced density matrix. I should pause and ask Marcus, how much time do I have?
I don't know if you are how close are you to the end.
Well, how should
Well, I mean, I think it would be probably good if you could
wrap up.
try to wrap up.
Okay.
And next time we can go to the questions.
All right. So let me then skip on this. And so we learn various curious properties of the entanglement entropy through studying their holographic dual. And many of these non-trivial properties are very easy to see using the holographic dual. There's also interesting uses of causal wedge that I won't tell you about. And you can, there's been more recent developments in using the entanglement entropy to try to understand how the bulk dynamics, the Einstein's equations, actually emerge from properties of the entanglement entropy. And in fact, even more radical conjectures that the entanglement actually is the underlying object that creates space-time, that the space-time actually emerges from this. This is known as this ER is equal to EBR by Susskind and Maldacena, and sort of previous work by Swinburne, Mark Gunstonk, and so forth. All right, so I hope I have convinced you that black holes are very fascinating and very useful objects that bear on many areas of physics, and that they figure a prominent role in these dualities. And I think we're just scratched the surface. There's enormous amount of physics yet to be learned in this subject. Okay, so thank you.
So let's have a few questions. And also, let me just remind people that if we don't have time for all the questions today, we're going to have an open discussion with Veronika, and I think we've moved it to 2 p.m. tomorrow. But so there'll be lots of chances then as well. But let's have a few questions. Jack?
So what is the exact status of the ADS-QCD correspondence? I mean, it's not a precise match to the CFT, right?
So quark-gluon plasma is the closest thing that it comes to a conformal fluid. Mm-hmm. It has very low ratio of viscosity to entropy density. It's not quite at the value, but there's many universal quantities that come very, very close. So people actually do use these transport coefficients in analyzing, I mean, comparing with a quark-gluon plasma. But it's not the n equal to 4 Superior mills that we have. But the name of the game really is not so much of getting the details of a specific system as understanding the properties. So there's many universal properties. Same thing for ADS CMT, the condensed matter thing. I think the biggest use is, well, the geometrization allows us to sort of classify what sort of stuff we can have. And in many cases in condensed matter, we haven't really come up with a full set of classifications of what we can have. So this might actually allow us to figure out where to, what other systems we should be looking for. So maybe we can even motivate what to, a constructive way to actually get new materials.
So you mentioned this story of fluids being dual to basically perturb dynamical black holes that are evolving, and then you had those bits about turbulence that we didn't have time to hear. But I'm curious, I mean, in classical hydrodynamics, I mean, turbulence is this legendary unsolved problem, right? And I guess you probably haven't yet solved it because we would have heard about that. But do you see some weirdness in the black hole dynamics in the bulk that?
Indeed, and this is actually very, very, very cute. So people started studying, to learn about turbulence, started studying black holes, and they discovered that, well, indeed, the horizons do exhibit turbulence, and they thought, oh my gosh, that we haven't seen in GR before. They went and looked at other black holes, our Schwarzschild black holes, and in fact, it turns out that even ordinary black holes have this weird type of property. Adams, Chesler, and Yu used it to sort of calculate the fractal dimension of the horizon, finding it to be 4/3 or something like that. So it's not that the horizon itself would be severely ripply, but rather that in this expansion, when you deform it, once you go past the sort of overall smoothness, at the next level, it has this property. But it's a very well, if you told this to a relativist 5 years ago, they would have thought you're completely crazy. And now they're doing numerical simulations.
This is some transient state
This is a transient state
lives
that the
as
black
some sort of
holes
substructure to the, and eventually disappears.
It eventually disappears. It eventually dissipates. It's not like the black hole breaks up or anything. So Lewis Lerner and company have studied this, and you can sort of look at the various modes in which the black holes shrink, and you see an initially exponentially growing the distribution of energy into sort of the low angular modes to the higher one. There's this sort of UV cascade where momentarily the black holes looks like it's sort of destabilizing until the thing sort of so in this transient state, it sort of looks like there's this growing thing with a cascade and everything until it sort of dissipates away. So it's quite fascinating from the GR standpoint. But
Yeah, it sounds like there is a lot more beyond what Thorne and Price said back in the 80s.
Oh, yes.
All right, well, let's thank Veronika again.